Namaste and welcome to this lecture on mathematical foundations for machine learning. We are in week 9 and we have been looking at the ideas of vector calculus. Basically we are looking at the ideas of calculus, and then we said, look, what happens, I mean, what is the idea of derivative, what are the rules for differentiation, and we looked at what is it to say a function in xy plane and what is it to say a function in xyz space or R3. We said that in case of xy plane, which is just going to be a curve, and in case of the xyz space, we said that, look, this is going to be what would you call it? It's going to be a surface, right? And since it's going to be a function of multiple variables, we are going to have variations along of the function along each of these axes, and we want to capture those variations. So we just really want to capture those variations in the sense that what happens in the case of single variable function. We know that if there is going to be a small disturbance or a nudge in, let us say, our input variable, there's what is the nudge that's going to be there, or how is the function going to vary for an incremental change in the input variable x. And now we said, look, that idea we can extend it provided we go to the a higher dimensional space. What we said is, like, if there is a function of multiple variables, then the variations are going to be there along multiple directions. So what we do is just look at variations in every direction, keeping all the other fellows constant, right? Say for example, you have x, y, a function of two variables, let us say z is equal to f of x comma y. We said that, look, okay, I want to study the variation of z for variations in the direction of x and y. You said that keep y constant, give a small nudge in the x direction, and figure out what happens to the function. Similarly, keep x constant and give a nudge in the y direction, and then figure out what happens to z. And that is exactly where we got into the idea of partial derivatives. Like, if you had seen, we have done this partial derivatives and things in the last class, right? And we defined a few things where we said, okay, before we even got into the partial derivatives ideas, we also defined something else. Wherever the function was constant, you called such curves that you get for a constant function f of x comma y is equal to, say, some k1. You said that you get what is called as a level curve, and a collection of level curves, we called it as contour. And then we went on to define the partial derivatives of the function. Then we did some examples, and now the time is ripe for us to look into the idea of gradient and directional derivatives. We will look at the ideas of gradient and directional derivatives in this class, and follow it up with functions, second derivatives and stuff in the next lecture. So the focus of today's lecture is just going to be the idea of gradients and directional derivatives. So let us look at what this gradient means. So we are going to look at, let us do a quick recall. So we recall the ideas from last class. So what did we say? Suppose I have a function which is going to map n variables to a real number, right? We can take a simple a function where it is going to map from R2 to R. Say R2 is going to be our xy plane to R, a real number, right? So we can look at that. So we listed the partial derivatives. So suppose we have this function where I am going to map let us say a vector x in Rn. That means we know the notation, we know what it is. This means this x contains n variables, namely n components, x1, x2, etc., xn, and these n components correspond to the n variables, in turn the n different directions that we have. And these n variables, the function is going to take this all these n variables here, and then it is going to return, let us say, so this is going to get mapped by the function to, let us say, f of x vector, which is a real number, right. This guy is basically a real number. And we took the example of norm of a vector. We said that the squared norm of a vector is basically a function which takes n components or n variables and then gives you a real number, right, that is the length of the vector. And we said that, look, we defined the partial derivatives as the following. So, the partial derivatives were given by the following. We said that dou f by dou x1, dou f by dou x1 is nothing but limit h tending to 0, limit h tending to 0 f of x1 plus h, all the other parameters, all the other variables, they remain the same, no change in them, minus f of x1, x2, etc., xh divided by h. And you can extend this idea to all the n variables. So, we are going to get f of, okay, dou f by dou xi is nothing but limit h tending to 0 f of x1 comma x2 comma xi plus h. So, this says there is going to be a small disturbance in the ith direction or the ith component comma etc. xn minus f of x1 x2 xn the whole divided by h. This is what we had. And now what we are going to do is we are going to do something interesting. We have got all the partial derivatives now. What are we going to do with these partial derivatives? How are we going to put all these partial derivatives into a structure, right? So, that is where we are going to do this. So, what we are going to do is we are going to collect all the partial derivatives, collect all the partial derivatives as a row vector. Now, what do we mean by this? We know the idea of vector, we know the idea of column vector, we know the idea of row vector. So, what are we going to do? We are going to do this. We are going to write this as, okay, put this as dou f by dou x1, then the second component is dou f by dou x2 and it goes on, then we have dou f by dou xn. So, it is just going to create a 1 by n matrix. So, this is going to be a single row of n components where each component corresponds to the partial derivative of the function with respect to that particular variable, right. Each column corresponds to the partial derivative of the function with respect to that particular column's variable. So, this is what we have, and this collection whatever we have is what we are going to call as the gradient of the function f with respect to this x vector. So, we are going to say this is called the gradient f. This is called gradient f or grad f. So, this is what we have, right, where we are going to say the following. We are going to say that, look, n is going to be the number of variables we just have one, what would you call, this one denotes the dimension of the image. If you remember what an image is, you have a function, you have the image of the function, the range of the function, the codomain of the function, whatever that is. So, that is going to represent the dimension of the function, and the x vector alone, remember this x vector is going to be a column vector x1 x2 etc. xn. That definition of our x being a column vector, that structure remains the same, we are not going to do anything, right. So, what are we going to do? Suppose I have a function, let us just take an example. Suppose I have a function which is going to map R2 to R. That means it is going to take two component vector to get you a real number. So, what are we going to do? So, we must remember that let us say I have this function f of x comma y. Now what does this mean? This f of x comma y implies it is a function of two variables, and we know that f of x comma y changes as x or y changes, right, x or y changes. So what do? We will take dou f by dou x in this case. This is going to treat y as constant, and dou f by dou y treats x as constant. But what do these two capture? These two capture the rate of change of the function in the x direction and y direction, right. Okay. Now just go on to extend this a bit, probe this bit further. So suppose I have this, let us just take a simple example where I am going to look at a surface. Consider a surface, what does that mean? I am going to look at z is equal to f of x comma y. So the if we want to bring it to the notion of a vector in R2, I am going to write this as z is equal to let me say z is equal to f of x y. So this is the this clearly says that it is going to be f of R2, the function is going to map R2 to R, right. Now let us just look at this, let us just take this case. Say suppose I have, let us say this is the vector which is let us say x comma y, right, this is the vector x comma y. Now we will have to understand one important stuff. Say suppose when you are on a mountain, let us assume that you are on a mountain at a particular point, let us say some mountain which is going to be like this, you are at this particular point, let me call that point to be x comma y, right, that is the point that I am going to look at as x comma y. If I want to view, if I want to look at from here at this point I stand and I want to look at some direction, I just want to look at some direction. Now how many directions are available in this case? So we have infinitely many directions, I mean you have many vectors there, right. So you can look at any direction that you want, right, you can have infinitely many directions. So from the point x comma y we have infinitely many directions. Infinitely many directions. For example, if you take R2, from here I can look at this direction, I can go in this direction, I can look at this direction, I can look at anywhere, right, I have multiple options being at a particular point, right. Now what is interesting is this is a surface that we have. If I mean again I tell you to look, I mean have picturize a mountain in your mind, I mean just have a visualization or a picturization of a mountain in your mind. Now what happens is when you look at when you stand at a particular point, you see that the surface, that is basically the mountain that you have, it has slope in all these directions, right. In some places it could be flat, in some places it could be, in some direction it could be steep, in some direction it could be a very what you call a slow growing function. It could, you could have a lot of you have slopes in all these directions. That is one thing which we need to really understand. So what we say is, we say that the slope or the surface has slope in all these directions. the surface has slope in all these directions. So what we want to do is we probably want to look at, we would like to know the slope in a specific direction, the slope of f in a specific direction. Okay, we want to look at the slope of the function or the slope of f in a specific direction. So let's just take a simple case. What are we trying to do here? So what I'll do is I'll take let p be the point which is x naught comma y naught, which is precisely the point that I had marked here. Let this be taken as, say, x naught y naught. Okay. Now what am I going to do? So what we are going to say is let the function f of x comma y be defined around this point P, defined around the point P. And we are going to have one more thing here. I am just taking everything in two components so that we understand it better. I mean totally you have like, we are operating in R3, but what is it that is happening? The function is going to take vectors from, I mean 2 component vector, and it is going to give you a what do you call a real number. So basically we are operating in R3, that is something which we need to understand. We are operating in R3 where the 2 independent variables x and y are taken to be the input variables, and z is the dependent variable along which you have your function to be plotted. So I have this. Now what I am going to do is I am going to call one more fellow. I am going to have define one more fellow. Let u equal to, say, u1 u2 be a unit vector. Let this be a unit vector. Okay. Now what are we going to do? I want to find out the slope of the function or the rate of change of that function standing at that point x naught y naught, but looking in the direction of u1 u2. Okay. Now let us just do a small recap here before we get to what we are trying to say. So what we will do is let us just quickly recall the derivative of a function of single variable df by dx. So the derivative of y is equal to simple f of x. That means this function is going to map r to r, right. This is going to map r to r. So we have df by dx, which is basically given by limit h tending to 0 f of x plus h minus f of x divided by h, alright. Now with a single variable this makes sense, but when I get to the idea of a vector, a 2 component vector, that means a function of 2 variables, this h does not make sense really, right, because h is going to be a scalar and x is going to be x1 comma x2 or x naught comma y naught or whatever that point that is. H is going to be a scalar, and it does not really make sense for us to add a vector with a scalar. It does not really make sense. Therefore I want to look at an incremental thing in some direction, right. So what we say is we are going to look at this. So in case of the multivariate, in the multivariable case we have this. In the multivariable case we have, let us say I will use this notation to say that df by dx vector, this collection of basically all the derivatives, is going to be limit h tending to 0, this is still there. I am going to do this f of the vector, let us say I have this x vector here which is going to have the components x naught and y naught, right, or x comma y, I am just going to call that as x vector, plus h times this u vector minus f of x vector, that means divided by h. So, what does this mean? This simply means it is the following: limit h tending to 0 f of, let us say, x naught y naught. We are going to look, we are standing at that particular point P, which is x naught y naught, plus h into u1 u2, h is a scaling factor for this u1 u2, minus f of x naught minus f of x naught y naught divided by h. This is what it is going to be, right. So, what does that finally boil down to? I will write it this way, it should make sense now. Limit h tending to 0, I have f of x naught plus h u 1 minus y naught plus h u 2 minus f of x naught comma y naught divided by h. I hope that makes sense, right. This makes sense. So, I am just going to write this as equation 1. Now, what I am going to do is I am going to just do a small trick here. I am just going to define another function, say g of h. So, these are all functions of h. Now, based on h things will vary, you have x naught y naught to be fixed. So, what I am going to do is I am going to define a function, say g of h to be f of x naught plus h u 1 comma y naught plus h u 2, right. Now, the moment I put this, the first equation, the one that I have labeled as 1 here, that equation becomes, equation 1 becomes limit h tending to 0. This is going to be g of h, the first term that I have is g of h minus, what is this f of x naught comma y naught? When will I get x naught comma y naught? When I put h is equal to 0, I will get x naught comma y naught. So, I am going to call this as g of h minus g of 0 divided by h, right. This is what I am going to have. So, this equation, this expression basically boils down to this upon this substitution, right. So, what does this mean? This is nothing but, if you look at, let me call this as, say, expression 2 or equation 2 here, the expression, let me mark this as 2. Now, what does 2 imply? 2 actually means, this means, what is that? Is the derivative of the function g, this the derivative of the function g at h is equal to 0. What does it mean? This actually means you are going to look at dg of 0 divided by dh, which is nothing but d by dh of f of x naught plus h u 1 comma y naught plus h u 2, right. This is what we have, right. And what is this evaluated at? Evaluated at h is equal to 0. Now, we have seen something like this before. You have d by dh of f of x naught comma h u 1. Let me call x naught plus h u 1 as x and y naught plus h u 2 as y. So, this is going to be a composition that I have. So, I can use chain rule here of the derivative. So, what I am going to do is I am going to say, let us say d. So, what am I going to do? I am going to write dg by dh is equal to dg by d. I am going to write this as, okay. Oh, let me put this. So, this is basically a function, in fact, 1 minute. So, d by dh of this, what we are going to get is, this is going to be the following. So, if you apply chain rule, what we get is df by df divided df by dx into dx by dh plus df by dy into dy by dh. And since we are doing partial derivatives, we could actually put this as dou f by dou x we have this following, which is nothing but what is df by dx? Df by dx basically gives the we'll write this as dou f by dou x into dou x by dou h plus dou f by dou y into dou y by dou h, which is nothing but what is dou f by dou x? That's basically the partial derivative of the function with respect to x, right? Partial derivative of the function with respect to x. So I'm going to give a nomenclature for that, notation for that. I'm going to call that as fx, where fx is nothing but dou f by dou x. What is dou x by dou h? Dou x by dou h is basically, this is going to be h, right? X naught is constant, you have h u1, so dou x by dou h is nothing but u1, fx into u1 plus what is dou f by dou y? I am going to give the same new notation here, which I am going to call this as fy into dou y by dou h is nothing but hu2, differential of hu2 with respect to h, which is going to be into u2, right? This is what we have. All these things which are basically evaluated at h is equal to 0. Yeah, have that in mind. So what do we get? We basically get, this is nothing but fx evaluated at, let us say, x naught comma y naught into u1 plus fy of x naught comma y naught into u2, right? We have this which is nothing but, let us say, df by dh or dg by dh. This is df by dh, where, yeah, this is df by dh, right? We see something very interesting here. What is that? This is of the form, let us say, v1 w1 plus v2 w2, and what is that? That is basically the dot product of the two vectors v1 v2 with w1 w2, right? That is the dot product of the two vectors, exactly what I have here. So what I am going to do is, I am going to write this as fx fy dot product with the unit vector u1 u2. What is this collection of partial derivatives? We call that as the gradient. So I am going to write this as del f with respect to x, del f x dot the unit vector, right? We have this. So what we are going to do is, we are going to say that we are going to give a name for this df by dh, we are going to give a name for this. So what we do is, in fact, if you look at this, this is going to be fx fy evaluated, okay, let me put this as x naught comma y naught, this also as fy of x naught comma y naught. Okay, let me rewrite that. So this is going to be fx of x naught comma y naught, then fy of x naught comma y naught dot product with this, which is nothing but dou f by dou x of evaluated at x naught comma y naught, dou f by dou y evaluated at x naught comma y naught, right? Dot product with this unit vector that we have already taken, the direction in which we are seeing u1 u2, right? This is what we have. And this basically, whatever that we have seen here, this is going to be the this is the guy, this guy is going to be my, what is that? He is going to be my gradient. So this is going to be my gradient. That is going to be gradient of f, right? So what are we going to do? This gradient dot product with u1 u2, basically says that look, I want to look at the derivative of that function, the slope of that function in that direction which corresponds to the unit vector u1 u2. Therefore, I have a name for this. I am going to give a new name for this. What is the name? We call that as the directional derivative. So, we say that we define the directional derivative of a function, directional derivative of a function denoted by d, I am going to say, of the function f with respect in the direction of the vector u as the slope, as the slope of the function f in the direction of u. Right. So, in general we have this, in general we are going to say d, the directional derivative of this function in the direction of u is nothing but dou f by dou x into u1 plus dou f by dou x dou y into u2. Right. Let us just take a quick example and then we will look at some interesting observations here. So, let us take some example, example 1. Suppose I say f of x comma y is equal to, let us say, x y. So, what are we going to do? We want to find the directional derivative, find the directional derivative of f in the direction of u at the point, because you are standing at a particular point and then looking at the slope in that direction at the point, let us say 1 comma 2 in the direction of 3 comma 4, the vector 3 comma 4, right. We are going to look at in this direction. So, first of all we must understand, so how do we do this? So, first let us calculate, let us figure out what are all the numbers that we have. Let us write it out clearly. F is equal to first x y, then x naught comma y naught, the point at which you are going to look from is basically 1 comma 2, then the unit vector that the u vector that you have is 3 4. Unfortunately, this is not a unit vector, therefore, from here I can get the unit vector by dividing the vector u by the length of the vector. So, I am going to get this is going to be 3 4 the vector divided by square root of 3 square plus 4 square, which is nothing but 1 by 5 times 3 4. That is the unit vector that we have. Now, everything is ready. Let us go ahead finding the partial derivatives. Let us look at dou f by dou x. Dou f by dou x is y and we want to evaluate at 1 comma 2. So, this becomes 2. Then I want to do dou f by dou y, which is basically equal to x. I want to evaluate this at 1 comma 2 and that is equal to 1. Then I want to get the directional derivatives now. So, I want to look at df in the direction of u, which is nothing but dou f by dou x, dou f by dou y evaluated at 1 comma 2, dot product with the unit vector u, which is nothing but we have dou f by dou x evaluated at 1 comma 2, which is basically 2, and this vector, this value is 1, dot product with the u vector, which is nothing but 3 by 5, 4 by 5. So, what do we get here? We get dot product, which is going to be 2 into 3 by 5 plus 1 into 4 by 5, which is going to give me 10 by 5 and that is equal to 2. So, that is basically the slope of the function standing at the point 1 comma 2 looking in the direction of 3 4. So, that is the slope. Suppose you change the direction, the slope will change, right. So, what are we going to do? this is, I mean, this is how you calculate. Now there is something interesting that comes out of here. What is that? Recall our definition of level curves. Recall our definition of level curves. Now what do we mean by that? In case of level curves, we have z is equal to f of x comma y, which is equal to a constant, let us say k. So when the function is a constant, what can we say about the derivatives? The derivatives are going to be 0, right. Therefore what we are going to say is, we are going to say that the directional derivative d, the directional derivative d of the function in the direction u, where I am going to say this, the direction is going to be along the level curves. So we are going to say along the level curves is 0. Most important understanding. So what does it mean? Say suppose we looked at that cone in 3D. So the level curves are going to be like this. The level curves are going to be concentric circles you are going to have. Bear with me for this drawing, it is going to be a bit bad. So along the level curves, what it says is, look, the function is constant, therefore the slope will be 0. Now let us also look at this one more interesting thing. So what did we do? We said the directional derivative of the function u is basically given by the gradient of that function evaluated at the point x naught comma y naught, right, dot product with the u vector. This is what we had, this was a vector and that is a vector, dot product with u vector. Now so this I can write this as the magnitude of this gradient vector at the point x naught comma y naught into the magnitude of u into cos theta. This is what we have. Now since u is a unit vector, we can say that the magnitude here is 1. So what I get is df, the directional derivative along the direction of u, is going to be just the magnitude of the gradient vector evaluated at the point x naught comma y naught cos theta. Okay. Now what does this mean? When theta is equal to 90 degrees, the directional derivative is 0, that we all know. When cos theta is 0, when theta is 0, 90 degrees, cos theta is 0, which implies df in the direction of u is going to be 0. Now we just saw that the along the level curves the gradient is 0, which means the direction of 90 degrees that we have, basically the gradient vector is basically perpendicular to the direction of level curves, that is what we have, right. So this says this is basically along the direction of level curves. Okay. What is the value that cos theta can take? Cos theta can take a value between -1 and 1, right. Now when will cos theta be equal to 1? When theta is equal to 0. When theta is equal to 0, cos theta is 1. Brilliant. So now what we have here, the directional derivative df of u is nothing but the magnitude of the gradient vector evaluated at that point x naught comma y naught, alright. Now when it is 0, what does it mean? The unit vector that you are looking at is also along the direction of the gradient. This implies the unit vector is along the direction of the gradient. and from one level curve to from the level curve this is going to be at 90 degrees. Therefore, what we say is, look, along the direction of gradient is where we are going to have maximum increase, right. So, we are going to say this is going to be the direction of maximum increase or direction of maximum rate of increase is along the direction of gradient. That we are going to call it by, you are going to say that, look, this is the direction of steepest ascent, direction of steepest ascent or climb. That means that is the direction in which you are going to have steepest climb, right, 90 degrees that you are going to get. Now, similarly, you can also have this, and you can actually look at a very interesting example that you can see here is probably you can look at a staircase where you see that along the levels of the along every step the height of the staircase is going to remain the same. Therefore, in the direction of the level curve we are going to have no change in the function. The steepest happens at, let us say, 90 degrees to that. So, basically that is where that corresponds to your gradient definition, the direction of gradient. And we know that when theta is equal to 180 degrees, when theta is equal to 180 degrees, cos theta is minus 1, right, cos theta is minus 1. So, what are we going to get? I am going to get the directional derivative of the function f in the direction of u when the unit vector is like 180 degrees in the opposite direction that you have. So, you are going to get minus magnitude of the gradient vector evaluated at the point x naught comma y naught, right, and this is going to be the direction of steepest descent, direction of steepest descent. And that is exactly where our idea about gradient descent algorithm, I mean that is where we actually look into the gradient descent algorithm. We do not look in the direction of gradient, but we look at a direction which is opposite to that of the gradient. That becomes the direction of steepest descent when you want to try to minimize a objective function and so on, right. So, we just make one more statement and then we will wind up this lecture. So, we will say that, look, so the vector grad f, the vector grad f, this is basically an inverted triangle, okay. You have names for this, you call it as nabla. So, the gradient of f, the vector gradient of f corresponds to direction of ascent and the length of the vector, the length of the vector gives vector grad f the steepness, right. So, we have all these things and this is basically the intuition of you have your gradient and basically the idea of gradient descent employs this fact that the steepest descent direction is opposite to that of the gradient, I mean basically the ascent. So, what you do is take a negative of this and that is what you will be using in your gradient descent algorithm, which will be discussed in the next week's lecture. So what we do is, on that note, we will wind up this lecture, and when we come back we will look at the rules of partial derivatives, and then we look at Jacobian and Hessian, which are very, very important. It's not something big, but the question of it's not being big is not in terms of I'm not talking in terms of the conceptual complexity and conceptual weight and all. I said it's just an extension of the idea of gradient that we have done. In that sense, I said, okay, look, this is what's going to happen. So when we come back in the next class, we will look at the idea of the rules for partial differentiation and chain rule, partial derivatives and chain rules, and follow it up with Jacobian and Hessian. Okay. Okay, so in this class we did extensively about directional derivatives. We also did a lot about gradient, and then we said gradient is the direction of steepest ascent, and then we look at the directional derivatives, and then we said that okay, you can look at the slope of the function. The surface can have slope in all the directions, and you just want to figure out the slope in a particular direction, so you looked at the directional derivatives and so on. And when we come back in the next class, we will look at rules for partial derivatives and chain rule, Jacobian and Hessian and so on. Namaste.